Welcome all to this 7th lecture of Principles of Statistics. Today we're going to finish the consistency section and we'll start with the asymptotic normality of MLE. So I remind you that we left it in a result in which, so there is a weird circle there. So we left it in a result that was telling us about uniformity, right? So about a uniform law of large numbers. And so let's prove this, which actually is not very complicated once we have this condition of the brackets, yeah? Because the brackets, what is going to happen is that if you think about it, the brackets are in some sense, compactifying, or is in some sense, the essence of them is that the calligraphic H can be viewed as some sort of compact, right? Because we have this family essentially of functions that is sort of covering, the whole of this calligraphic H. Yeah. And so once we have compactness, well, compactness is no more than, the the uncountable version of a finite set, right? And so if, we saw that for a finite number of functions, you can prove, almost sure convergence of this maximum, then it should follow that we can prove it for compactness. And this is a very, very, this is a very typical way of arguing things for mathematical statistics. Yeah. Okay. So how do we go about this? Excuse me. Okay. Right. So proof. So the proof then of this result of the uniform law of large numbers is as follows. So let's start with fixing some epsilon. Okay. So we're going to show almost sure convergence. So then let's choose, rather than choosing an n, so rather than choosing a covering that, for this epsilon, what we're going to choose is for epsilon half, so that, the numbers sort of come out, to be what we want. So sort of nicely, these kind of things in math. So choose n, this capital N, for a covering with epsilon halves rather than epsilon. Of brackets, of course. So covering our calligraphic H. Okay, so same notation. This would be some H's J with the underline and overline, right? Okay, so let H being this calligraphic H be arbitrary. Okay. So then let us look at the quantity we want to look at. So the quantity we want to look at is really this guy, or the absolute value really of this guy, right? And it's going to be from 1 to n of h xi minus the expectation of h x1, if you like, for all of them. Okay, so so as I said, we want to look at the absolute value. So let's just maybe start with the quantity itself, and then we can think about sort of low bounding this. Okay, so how do we lower bound this? Upper bound this. Well, the most immediate thing is to bound the first h by the upper element. So let this bracketed, or maybe we should add here bracketed by, say, this j. Yep. So we know there exists a bracket. So what I'm fixing here is really just the j. Yeah. So the bracket. So then this guy is going to be bounded, as I was just saying, by this hj up xi, and then we can add and subtract, the expectation of this guy. And now what we are going to get, that's 1, is, let me just erase this little thing. Okay. So then, if we look at just this value here, or this, this difference here, then this is very clearly bounded by, so we could have done this earlier, but okay, we could have lower bounded the h, in this expectation already by the hj underlined. Sorry. Okay, so then this is just this guy minus this guy. Yep, and in absolute value. Yep. Okay, so now by assumption, because we took, these brackets to be corresponding to this epsilon half, then this guy is less or equal than epsilon half. Yep. Okay, so then we're left with this quantity here. But this quantity here really, by the strong law of large numbers, it will convert to it will convert to 0, right? And so really, let's look here. What we really need is some sort of uniformity over the j's, but this is a finite set. Yeah. So by last lecture, what we have is that on an event, so we have this almost sure convergence for the maximum, and so this means that we have an event of probability 1 in which there exists an n naught, depending on the epsilon, of course, such that for all n larger or equal than this n naught, we get, what I was saying about the maximum, so this j being less or equal than this capital N, for the h j hat, for the mean. So let's see, mean over n, sum from 1 to n of this h j x I upper minus its expectation, right? Okay, and what we know is that this is bounded by epsilon halves. Okay, so we can bound it by that. We can bound it by any quantity. The n naught just has to become larger and larger as we have, or whatever it is, right? Okay, so that we're basically done. Yeah. So what we have is that, therefore, on this event, we get that 1 over n of the sum of these guys is then bounded by epsilon. Yeah. So now, by the same reasoning, we have that this guy is bounded above by minus epsilon as well. Okay, so you can do this. And this is, of course, in a different event, but it's still a probability 1 event. And so really what we have is that on a probability, right, so in the intersection of two events of probability 1 is an event of probability 1. So on a probability 1 event, when I'm saying event, I just mean a set of events. So maybe I should say just on a set of probability 1. Probability 1 set, we get precisely that, the absolute value of this guy is bounded by epsilon. And now remember that this is for H arbitrary. And so then we get that the same is true. And so the soup over H, this thing is also bounded by epsilon. And so we're done. Yeah. So it's not really very hard. Yeah. And this idea of, essentially have a compact. Yeah. Okay, so let me now give the proposition that we really needed to prove consistency, and I will not prove it. So I've decided not to prove it, also because I received an email to which I will reply soon, talking about this measure theory ideas, and whether this course is very much it has a lot of topology or probability and measure. I mean, I will not be expecting you to be attending probability and measure, and so really whatever really belongs to that course is belongs to that course, not this one. So in some occasions it's true that I'm going through the proofs very carefully in terms of the measure and this kind of things. I guess this is just my taste, but I will not expect you to be totally on top of that. So I mean, there are some concepts that you should be aware of. So for instance, someone emailed me as well about saying, well, a question that basically came down to saying, oh, why are the PDFs of parameters that are different in an identifiable model, why are they equal almost everywhere? So then, of course, that comes from the fact that I assumed that the distributions for two different parameters must be different, and that in itself, if the reference measure that we're talking about is Lebesgue, so that's what you need for a PDF, then it implies that the densities must be equal almost everywhere. And these kind of things you don't need to know for this course. So I'm just talking about them because really, I would assume that a lot of people are going to probability measures, so the majority are going to it, and and this kind of proofs really sort of require those kind of ideas. Yeah? But again, if you're not attending that course, you can sort of try to understand what I'm saying, but also skip whatever is probability measure. Okay, so I don't know if I sort of answered all of the questions that I was being asked. Oh yes, so regarding topology, so this person, the first email that I was talking about talked about topology, and I mean, a topology is a bit unavoidable, right? I mean, it's not like we're using a lot of it. I mean, we're just talking about compact sets and continuous functions and this kind of thing. So you really should be on top of that, I think. Not because I'm planning to ask anything that is as theoretical as this, but because that's just sort of analysis. So topology is the basis of analysis, and then analysis is the basis of probability, and probability is the basis of stats. So, sort of it just follows naturally. Okay, so so let me just stop chatting and get on with this. So proposition. So let's now state proposition 3, which is, as I said, what we need. So let's assume, and this is something we sort of already spoken about, this guy is compact and as usual in RP, and that Q, which is a function with two arguments and real valued, is measurable with respect to, measurable in X for all theta here, and continues in theta for all X in the calligraphic X. Yeah. Okay, so then assume also the usual thing that, what we were sort of having in mind, which is that the expectation of the supremum of the parameter space is finite. Then we have what we wanted, which is this uniform convergence over the of the parameter space here. So it would be just this on the Bren, and the sum xi minus the expectation of any of them. So that's just one. So for instance, sorry, this is going to 0 almost surely, and this is of course. Okay, so I mean we're assuming that we have this sample, yeah. Yeah, so we assume that. Yeah? Okay, so yeah, so we have just the usual product, infinite product probability measure. Okay, so for the proof of this, again, I just said I'm not going to cover it. So C, I will post a handout today or during the weekend. Handout, in case you're interested. Handout, including the dominated convergence theorem. And of course, this is not an example. Okay, so, right, enough. For consistency, let's look at, something that is stronger, which is the asymptotic normality of the MLE. Okay, so we sort of, well, actually, let me give you a definition first of all. Yeah? So definition 4. So we say that in a, I guess, statistical model, in which we have that the well, we have a consistent estimator we say that it is, this consistent estimator is asymptotically efficient if, now remember, being consistent just means convergence in probability. This is n. So as you get more data, then what we're now going to look at is the variance of this guy. So the variance of this guy, that's going to converge to 0 because the guy is converging to something, so to a non-stochastic value. And for efficiency, we need that rate to be square root of n, in terms of the estimator, or n in terms of the variance. And to actually be, efficient, we want it to be a very particular value. This guy, for this guy to converge to a very particular value, which is exactly the one that you're probably expecting, and it's just a Fisher information matrix that we spoke about. We sort of touched upon this already. Okay, so what we are going to show now is, so we now show that the MLE is asymptotically efficient and more. Yeah? So we show that in a so-called regular parametric model, and I will give you now the definition of this regularity, of what we mean by this, and this is just a yeah, okay. So I will give you this in a sec. So in a regular model, we have that square root of n theta n, or MLE hat minus a theta, converges in distribution to a normal distribution with zero mean and the inverse Fisher information. And this is, of course, for all theta in the interior and also under, let me write it there, under p theta. Yeah, so just the usual product measure. Okay, so let me maybe just comment. So this, by the way, implies the, some sort of universal. It's not universal because you need the regularity, but nearly. This is like very, very broad assumption. So universal distributional approximation given by theta MLE being approximately like a normal distribution, but its distribution being approximately a normal with mean theta and variance again converging to zero, but with this constant. Okay, so that will be very useful for asymptotics, for inferential procedures, and we will see this later on. Okay. So let's now talk about these regularities or the assumptions. And so let me now introduce assumption B. So we had assumption A for consistency, and then assumption B. We're going to assume, so again, this is an assumption on a model. So let's see. So we assume that the statistical model, F theta in here of PDFs or PMFs so we say, and again, as usual, on RD, yeah, satisfies that for all theta naught in the interior of the parameter space, we get the following. Yeah? So the following four assumptions. So first of all, that there exists a neighborhood of this theta naught. So there exists this open ball. This is within, of course, within the parameter space, such that theta naught, so as I just said, this is a neighborhood, is there, but also such that this function, so fx theta, is, so remember that for consistency we had continuity, but actually after showing continuity we talked about simple proofs for using differentiability. So now what we're going to directly assume is twice differentiability. Yeah? So twice differentiable on U for all x fixed, yeah, in this calligraphic space. Now B2, well, remember observation 2, we had the following assumption. So we had that the gradient with respect to theta, and this should be with respect to theta naught, log of fx theta naught squared is less than infinity. So that's just what we had already. And then additionally, we're going to assume that the expectation and the theta naught of the Hessian of this guy, the Hessian again is with respect to theta, so theta naught, that this guy is non-singular. Okay, so this guy is essentially the Fisher information matrix. Yeah. Okay, so B3, we have some I guess technical conditions. By the way, all these conditions, you do not need to learn them as part of the theorem of the asymptotic MLE, asymptotic normality of MLE. So asymptotic normality of MLE, you should definitely learn it in the same way that you should learn consistency, but it's in the statements, but you don't need to know the exact assumptions. So the exact assumptions are there so that we have a you know, a rigorous proof for this, yeah? And so that you get an intuition as to what is going on behind this. So then the assumption is that there exists an R, you know, a positive real number that so that this ball, so that, you know, basically what we are assuming is that there is a closed ball. So this would be theta minus theta naught. Remember, we fixed the theta naught above, and again, so this closed ball such that this satisfies, or such that, okay, so such that maybe, let's say, for we have the following conditions. So the supremum over the k of the Hessian log is less than infinity. And then we also have two assumptions that have to do with, well, okay, so I'm going to state them, by the way, for the continuous case, but again, you know, think about what would be the condition for a discrete, so for a PMF rather than PDF. This is f x theta dx, so that should be lowercase. Okay, so this is less than infinity. And then the other one is that, so again, you don't need to learn these, but we will use them. Supremum of this k of the Hessian of f, again, theta, so that this is also bounded. Okay. Is infinite. Okay, and then the last one is that we have consistency, essentially, but at least for the interior. So if x1, x2, and so on are IID according to f theta naught from, you know, theta naught from before, then the MLE theta n hat, or MLE, exists, and it satisfies that it converges to this theta naught in probability. Yeah, this probability is, of course, cannot be under anything else. Yeah? Okay, so, well, let's just write it just for clarity. So essentially what this is saying is consistency in the interior. So consistency would generally include all of the parameters in the parameter space, but we don't need that. Yeah? Because we're interested in the interior, because otherwise out of the interior, the asymptotic normality of the MLE is not true. Yeah? Okay, so let me now state a fact that you should think about, because essentially this is something, maybe let's call it a lemma. This is something we've basically spoken about, and is probably a good exercise if you like this kind of stuff. So then say that observation 2 and proposition 1 they follow from so I think this would be A1 and B1, B2 and B3. Yeah. Okay, so we're now ready to state asymptotic normality of the MLE. So we have okay, so in the theorem we wish, as usual, this model to be this guy to satisfy the assumption, but also A1, yeah, and A2 and B. Okay, so what can we say? Well, let's get some data. So if x1, x2, and so on are, IIDs, are just as before, according to theta naught, and then for some theta naught in the interior, and this is really important. You will see in the example sheet examples in which it's not true that the MLE is asymptotically normal if it is not in the interior. And this MLE be, well, let this be the MLE or an MLE. Okay, so then what we get is, I don't want to break this, so then we get what we were sort of claiming before, which is that this is going to converge in distribution to a normal distribution centered and with the inverse Fisher information of the theta naught, and this should be under P theta naught. Yep. Okay, so that sort of makes sense. Okay, so we're doing pretty well in terms of time. So I think the rule is that overall I teach 24 times 15 minutes or around that. So we'll end a bit earlier as well again today, but that should be okay because then we'll probably use more time in future lectures. Okay, so let me, rather than proving this, because we'll prove it in the next lecture, let me just give you a proof idea. Yeah? As a warm-up. So proof idea, and this is for P equal 1, so one dimension in the parameter space. So due to the consistency of the MLE, this converges in, okay, so maybe let me just write, by the way, let me define, so let PR be precisely this P theta naught with the infinite product measure. Then due to the consistency that we were talking about, this is going to converge under this measure to theta naught. And what we get is that because the theta naught is in the interior, then really this guy is going to also be in the interior of the parameter space, with high probability, by which I just mean, in sets of probability converging to 1 as we get more and more data points. Okay, so because we're now in the interior, then we can apply Taylor's theorem or the expansion, and we have that. If we look at the normalized log likelihood, then we know that its derivative at the MLE is 0. And so let's expand it because we have second differentiability, and let's do so around the theta naught. So this is going to be, let me just think if I'm placing this correctly. So, okay, so let's just do this, and then we have, the usual quantities. So this is some tilde and the MLE minus the theta naught. Yeah. Where, of course, this is some intermediate value. So this is some eta or maybe xi theta MLE. So remember, this is one dimension, by the way. Okay, yeah. So for some xi in 0, 1. Yeah. Okay, so now really, all we need to do is, remember we're looking for the asymptotics of this difference. So really, if we can take this guy to the left-hand side and invert that one, then we're sort of pretty close. Yeah. So then assume, so if this guy is distinct from 0, then, you know, we're going to have that. Let me just make some room here. So what we're going to have is that, again, so as I was saying, the MLE hat minus theta, we can solve for it and get the negative second derivative inverted at this guy, that is an intermediate value, -1, and then the ln prime at theta naught. Okay. So, and really, of course, we want to look at square root of n of this, so we can add the square root of n there, the right hand side. And really, it's just a matter of arguing for the two of them, you know. So essentially, this one, you know, that guy is a bit annoying. But if you had a non-random value, so if it were just theta naught, then this would be pretty simple, yeah, because this would all go to the Fisher information matrix, right? So essentially, we will prove that anyway, yeah. And so we will show that, and this is by observation 2, maybe a bit more, and yeah. So this will be, I guess, in probability. And then what's going on with this other guy? Well, this other guy is actually a pretty nice quantity because the normalized log likelihood, really, we can write it as this. So here's the log f xi theta, but not. But we can subtract its mean, yeah, because its mean actually is just simply 0, right? So this is log, yeah, of f xi theta naught. Yeah. Okay, so yeah, okay, I knew I was missing something. So this is the derivative, yeah, with respect to theta, and this is the derivative with respect to theta, yeah, because this guy is 0, yeah. And so then this whole thing will go, you know, by the central limit theorem in distribution to a normal distribution with 0 mean and variance equal to the Fisher information matrix. And so now we can use Slutsky's lemma to say that the two things multiplied together, so remember this is a -1, they will give us that, you know, the product converges to a normal distribution with 0 mean, and then, you know, this guy, this guy, this guy, and so, you know, what we wanted. So this is sort of very informally how the proof goes about. Yeah? And in the next lecture, we go into really sort of prove it carefully, yeah, with the assumptions that we've given. Okay, well, I hope you enjoyed the lecture, and to see you again next week.